So, last time I had just stopped at this slide where I described just about described the equivalent of the population inversion in case of a semiconductor laser. Okay. So, we had seen that this EFC and EFV, the difference between these two should be greater than the lasing action that is here. Okay, that is happening here. So, I had stopped at that, and I did not describe to you what a PN junction looks like. So, this is a schematic, no doubt, but this is what a 3-dimensional picture of a semiconductor laser will look like. So, this is the laser light here shown in yellow, and this is the depletion region shown in green and going all the way here, and of course, this is the anode and the cathode. Now, in case of lasing action, so we need mirrors on the two surfaces. So, what is generally done is, like here I have written as cleaved surface. So, this surface is cleaved, even this surface is cleaved, the one parallel to this. Okay. These two surfaces are cleaved. Now, what is meant by cleaved? Cleaved is, you know, a special way of cutting absolutely parallel to the parallel surfaces, or maybe you can say perpendicular to this surface. Okay, this is exactly perpendicular to this surface. So, when it is cleaved, it gives you a mirror like quality. The semiconductor laser is such a tiny object, the semiconductor itself, that putting separate mirrors is out of question. And sometimes some of these surfaces can be coated to give a higher reflectivity, but generally they are cleaved, and this surface is made rough, so that no light comes out from here. All the light should, the lasing action and the lasing light will come out from here. Okay. So, that is what is meant by cleaved surface. Now, in case of a cleaved surface, what happens is you do not get very good reflection, not 99% reflection. You get somewhere around 30% reflection. So, 30% of the light that is coming to this one surface is bouncing back into the semiconductor to gather up more stimulated emission and the lasing light itself. So, that you would say is terrible as far as lasers are concerned. But then the advantage in case of semiconductor as compared to the other lasers is it has a very high gain coefficient. Because of that high gain coefficient, even a slightly less reflectivity is okay. The gain coefficient, the high gain coefficient makes up for the loss here, and that is how the lasing action takes place in this case. And most of the time it is around this depletion layer here, okay, and it will be a strip of light coming all along this strip. It is not a nice round circular thing that is coming out, it is coming out like a strip, and you will have to put other kind of optics in case you want a circular cross section beam. Okay. So, that is what the semiconductor laser is like. So, let me tell you something about some of the types of semiconductor lasers. Okay. So, you could classify them as low power lasers here. Okay, some of the uses in terms of, you could say low power, mid power level and high power lasers. So, in case of low power lasers, its uses are laser pointers, data storage, okay, barcode readers. Okay, so, this barcode readers, if you have noticed, it is always a very thin strip of light, which is, it is a strip of light that comes out. Okay, there you need not put the actual output of the semiconductor laser is used in that barcode thing. No extra optics is used to get a circular beam or anything. Okay. So, that's for the barcode reader. Then you have the fiber optic communication system in which this low power lasers are used, where only the signal is important, you know. So, that's why it is there. And then in CD players, if you've I do not know if you've noticed, so it's like the reader, you know, it reads the CD, okay, the laser. Then you have this mid power laser, which are used in display systems, maybe in the entertainment industry or general lighting, sharp lighting. Then in some medical applications, medical applications also generally like hair removal and skin color tone differentiation, those kind of medical applications are used because it's just mid power, it doesn't have, it's not a very high power thing. Then a very important application is the LiDAR. LiDAR, that is light detection and LI stands for light detection and ranging. Okay. LiDAR stands for light detection and ranging. That means it is like a sensor, it senses the distance of objects. Okay. So, you can use a laser for that. So, you really do not need a very high power laser for such an application. So, sensing once again here, LiDAR and sensing, other sensing thing, and then projectors. Then high power lasers of semiconductors is used for cutting, welding, a pump laser for other lasers. That means it acts as a pump for say titanium sapphire laser, it acts as a pump for ND glass laser, you know. So, it's a source of light at a particular frequency. Okay. But generally speaking, semiconductor lasers do not go up to very high powers, and of course, it cannot compete with other, say, other lasers as far as power and the quality of beam goes, which applications like cutting and welding will really, the semiconductor laser will be outstripped by all, say, gas laser or other solid state laser which I have described before. Okay. So, semiconductors again, you know, to make it high power itself, you have to cool it, get a separate sort of a apparatus in order to cool the semiconductor itself. So, it is not always a viable option in case of, say, cutting and welding, though high power semiconductor lasers have been used for cutting and welding. So, here I just give you a sense of what kinds of semiconductor lasers are made, and quite a wide ranging. So, suppose I have this material, gallium arsenide or aluminum gallium arsenide. These two materials are used and they will give you a wavelength range in the 750 to 950 nanometer. Okay. And the output power will be in the range of 1 to 10 milliwatt. So, it is not really very high. You will get a low power like this very naturally without doing anything special for the cooling system of the laser, but it can also go up to several watts. Okay. When you put in all these extra systems to cool that laser or do a separate kind of doping of the material, and you can go up to several watts, but this will be the most natural output power. Then you have the indium gallium arsenide phosphide, INGAASP. Okay. So, these are all kind of gallium arsenide based PN junctions, you know, P type and N type has been doped with all these dopings of indium and phosphide. And so, you get a wavelength range in the 980 to 1550 nanometer. Again, this will give you a natural output power of 10 to 20 milliwatts and can go up to 1 watt with addition of special systems. Then you have the lead salt material. Okay. These are or quantum cascade lasers also. The lead salt material is made of lead, SNTE, Pb, Se, Se is selenium, and then you have this quantum cascade lasers which are in the infrared region 2 to 10 micrometer, and they will give you a wattage of 10 to 100 milliwatts, and that is how it is. We can go up to a few watts too. Similarly, gallium indium phosphide will give you somewhere in the red region 635 to 670 nanometer. Then gallium nitride will give you in the blue region also depending on the doping, or in the green region too, and an output power from 5 to 10 milliwatts. So, if you have noticed here, many of them and in the UV region you have this aluminum gallium nitride, this comes in the UV region. So, you have, if you have noticed that most of them are based on this gallium arsenide, though in semiconductors we do hear of silicon as quite a popular semiconductor, but it is not popular for lasers. It has its other uses in the semiconductor domain. But why? Because gallium arsenide, it is a direct band gap semiconductor, and silicon is not a direct band gap. What do I mean by direct band gap? And I have said before that in case of a direct band gap, the probability of photon emission and therefore lasing action is more probable, is higher, probability is higher. So, this is called a direct band gap. A indirect band gap, which is silicon, will look something, the energy diagram will look something like this. Okay. The K levels of the topmost of the valency band and the bottommost of the conduction band are different in case of indirect. So, in case of indirect band gap, the probability of light emission is quite low. It is not 0, it can take place in some cases, but you know there is an involvement of a third party, that is a phonon. Okay. I will not get into the description of phonon, but just remember that since silicon is an indirect band gap, the probability of lasing action is very low here, while in case of gallium arsenide, it is a direct band gap. That means the K values of the lowest and the topmost is the same. Okay. So, this is that is the difference between these two. So, before I end this topic of semiconductor lasers, let me give you some advantages and disadvantages. Though I have spoken about them intermittently during the lecture, but here it is kind of tabulated out. So, in the advantages, it is a compact size laser and it is portable, which you have guessed till now. It is a semiconductor, so it is very tiny, and it has a very high efficiency. Okay. That means conversion of electrical energy to light energy is about 30 to 70%. Okay, that is a big advantage over the other gas or solid state lasers. Okay, it does not have such a high conversion of electrical energy. Direct modulation capability, that means you can modulate the power and modulate the wavelengths also to certain extent by just varying the current. Okay. And it has a wide range of wavelengths that as you have seen in the previous table, it does have a wide range of wavelength, and low cost and mass produced, that is a big advantage. Then durability and reliability, no moving parts, that is why it is more durable and more reliable. It is just a piece of semiconductor and you are passing electrical current through it. So, no moving parts, that is what makes it more durable. So, these are the advantages. Now, if I talk about the disadvantages, actually the biggest disadvantage is that it does not have a good beam quality. You know, the beam quality, the beam that comes out is like a strip like this, or maybe an ellipse. You know, this is the cross section of the beam, while most other lasers will give you a circular cross section. So, this can be focused very easily, while the focusing of this is not that good. So, you will have to use multiple lenses, different types of lenses, in order to get it to a circular shape. So, this is actually, I think it is the biggest disadvantage, but okay, there are some other disadvantages too. Temperature sensitivity affects the efficiency and output power. Okay. Limited output power as compared to other types of lasers. Then the beam quality, as I have said, is not good. Output beam is a strip or an ellipse, and then degradation over time. Yeah, here okay, it is a durable laser, but then there is degradation over time to lesser efficiency and lesser output power. This may be true about many lasers, most lasers, but in this case perhaps again it is mass produced. So, in this case maybe the degradation and lesser efficiency is faster. Okay. So, and here complex cooling requirements. You need complex cooling requirements, specifically if you are going to a higher power output. So, naturally if you keep it to the low power output, maybe you do not need such complex cooling requirements, you do not have that kind of a requirement. But in case of case of higher power, you have to have this cooling requirement. Okay. So, these are the advantages and disadvantages, and I stop here as far as the semiconductor laser goes. But now, till now I have been speaking about low power laser. In my next few lectures, set of lectures that will come, I will speak about high power lasers, very high power lasers and its uses. The best use of a high power laser is in inertial confinement fusion. Okay. This is like bringing about fusion. You may have heard of fission. So, fusion is another nuclear process. Okay. And lasers are helping to bring about fusion, which is supposed to be very clean energy, clean and green energy, and radioactive waste is minimum as compared to the fission type of energy extraction. Okay. So, I will be dealing a lot with this inertial confinement fusion, in short ICF. You will slowly begin to understand why it is called inertial confinement fusion, but it is brought about by lasers. Okay. Laser is the I think there is another way of bringing about fusion, which is called the tokamak, which has been much older than the laser induced fusion. But in case of lasers, as they started developing in time, over time, and started gaining more and more energy output, people found the use of this laser in laser induced fusion. Okay. So, here what I show is, so let me speak a bit about what I mean by fusion. You have to recollect a little bit of your nuclear physics class or nuclear physics course that you have taken in order to understand this. It is very simple nuclear physics, nothing fancy, but just recollect a little bit of some of the terms that you had used in your nuclear physics class. Okay. So, here what I show is this is the nucleus consisting of protons and neutrons shown in different colors. Okay. Only the nucleus, I am not showing you the electrons which are revolving around the nucleus, only the nucleus, because fusion energy will come only from the nucleus. Okay. It has nothing to do with the electrons outside. So, we must understand this nucleus a little bit more in detail. Okay. So, this nucleus consists of electrons and neutrons, and you would think the protons which are here, say if I say the red ones are the protons which are here will should, you know, they are positively charged, okay, and they should just be flying apart. Nothing happens to the neutrons. Neutrons are neutral, they do not have any charge. So, the protons, because of the Coulomb energy, it should be just flying apart, but that does not happen. The nucleus exists and these protons exist with the neutrons. So, I am sure there must be some other kind of force which is different from the Coulombic force. Okay. So, this force is generally a short range force and it is an attractive force, and it is an attractive force between these nucleons. If I call protons and neutrons both as, I term them as nucleons. Okay. So, it is a short range attractive force which is keeping them bound together. Okay. It is all these nucleons are bound together. So, the proton and the neutron are attracted, the proton and the proton are attracted, the neutron and the neutron are attracted. So, they are like just individual neutrons. You describe them as neutrons and there is an attractive force and there is a binding energy which is binding all of them together. Okay. So, I introduce the term binding energy here, which I am sure you would have heard before in your nuclear physics class. Okay. So, what is binding energy? Binding energy is actually the energy required to throw apart this nucleus into individual nucleons. That means how much energy do you have to give to this nucleus so that these nucleons just fly apart. That is the binding energy. Okay. So, in suppose I give you an example, I have just put down an example here. The binding energy is calculated from Einstein's mass energy relation, E is equal to mc square. Okay. The total binding energy delta of a deuterium nucleus. I specifically take the example of deuterium nucleus because generally deuterium is used in fusion. Okay. So, deuterium is nothing but hydrogen with two isotopes. Generally hydrogen has one proton and one electron outside, and we are not talking about the electron in any case. So, it has one proton and one proton only in the nucleus. But deuterium has a neutron also. So, 2, if you can see 2. So, it has a proton and a neutron. So, it is an isotope of hydrogen. Deuterium is an isotope of hydrogen. So, here I am, I should calculate the total binding energy given by delta. So, delta will be the mass of the proton, mass of the neutron, okay, multiplied by the number of protons multiplied by the number of neutrons. Z and N are the number of protons and neutrons, okay, and minus the mass of the atomic nucleus. Ma is the mass of the total thing together. Okay. This consists of Z and N here, and each separately I have taken the mass, and Ma is the mass of the total thing. So, if I take these individual masses and minus it from the mass of mass of totality, then I will get this delta function. So, here I have just written down ma is mass of the atomic nucleus and c is the speed of light. So, mc square c square, and the masses are generally given as AMU in terms of AMU. 1 AMU is equal to 1.661 into 10 to the power minus 24 grams. Okay. So, this is 1 AMU. So, here what I have written are all in AMU. Okay, MP I have put it as 1.00728, this is in AMU. Then MN again I have put it in AMU. Everything I have put in AMU and then multiplied by this in grams. So, you get a total energy, that is the binding energy in ergs, and then if you convert it you will get it in MeV, million electron volts. So, delta turns out to be, in case of deuterium nucleus, 2.23 MeV. Okay. So, this was just an example, but on this left hand side you can see this is called the binding energy curve. It is a very famous curve. You will see it in all textbooks on nuclear energy. So, this gives on the x axis, it gives the mass number in terms of A, that means the total in the nucleus, and this is the binding energy per nucleon, all given in MeV. Okay. Here it is going here, and you have a curve which is something like this. Okay. That means it goes up, that means the binding energy increases as the mass number increases, but then again it slows down when the further down the line of the A increase. So, this is the, initially you are going up here and here you are coming down. Okay. So, the most stable element is at this point. Why is it most stable? Because the binding energy is the maximum. That means the nucleus is bound together very closely, and that element is iron. Fe, which has a number of 56 as far as I remember, yes. So, this Fe is the most, and it is most resistant to break up or to decay. Okay. While all on this side, on the left hand side and on the right hand side, they are all prone to breaking up or prone to decay. And why do they decay and why do they break up? Just because, or why do they fuse or break up, whatever, they are all tending to be this most stable nucleus. Okay. So, that is the importance of this curve.